Hello everyone, it's Tate here, and today we will be going over the Unit 4 MCQ. So let's get started. Alright. A student must determine the effect of friction on the mechanical energy of a small block as it slides up the ramp. The block is launched with an initial speed v initial from point A along a horizontal surface of neglectable friction. It then slides up a ramp where friction is not neglectable, that is, inclined at angle theta with respect to the horizontal as shown in the figure. The student measures the maximum vertical height h attained by the block while on the ramp, labeled as point B in the figure. At point B, the block comes to rest. The student performs 3 trials with the ramp at different angles, launching the block at the same initial speed v initial for each trial. The results from the trials are displayed in the table. How should the student use the data collected and the known quantities from the experiment to determine the initial total mechanical energy of the block ramp earth system for all trials in the experiment? Well, first thing we can notice is that this is certainly a wordy question. And so let's break it down. I think that's the best way to go about this. Oh, oops. Okay. So it's launched with an initial speed v initial. It slides up a ramp where friction is not neglectable. The horizontal surface is of neglectable friction. The student measures the maximum vertical height attained by the block while on the ramp, labeled as point B. At point B, the block comes to rest. The student performs 3 trials. Okay, so essentially what this is saying is that there's no friction here, but there is friction here. And when it says at point B where the block comes to rest, it's because of the friction on this ramp right there. So now we're trying to determine the initial total mechanical energy of the block ramp earth system for all trials in this experiment. So let's look at answer choice A. So use energy equals to work, which equals the force times displacement for all trials because a block traveled a different distance up the ramp in each trial. So first, we would need to consider the initial energy of the system before the block reaches the ramp to determine the total mechanical energy of the system. So the same amount of work is not done on the object by the force of friction in each trial. And we can explain this because we have different angles right here. And so if we were to use sine theta to find h, obviously the greater the angle gets, the larger sine becomes. And so this is not the right justification, nor is it the right equation, because it does not relate to the initial total mechanical energy of the block ramp earth system. For part B, use the gravitational potential energy is equal to mg times the change in y for all trials, because the block reaches a different height above the ground in each trial. So the first thing we can note is that this equation does not use enough information. So the total mechanical energy is supposed to be the kinetic energy plus gravitational potential energy, but this equation only gives us the gravitational potential energy while we only know the quantities from what's given in here. So the only thing we know is that delta y equals to h, and that we know that g is equal to 9.8, but we don't know the mass. So this question doesn't make sense because we don't have enough information collected to use this equation. Use the work of friction. The force of friction is equal to gravitational potential energy for one trial. Because the same amount of work was done by the force of friction in each of the trials. So the same amount of work is not done in each trial because the angle changes, and as we explained earlier, with the greater angles we have a greater amount, so this is wrong. So why is k equals 1/2 mv squared for one trial? Because the initial speed is the same. So we know that it will always be launched with v initial, and but v initial is not equal to v squared. V initial would actually be for the ramp, neglecting friction force, it would be v sine theta. And so because of that, as the angle increases, if we draw a unit circle, as the angle increases, the y is increasing, meaning that sine is increasing. And since we're plugging it, it's directly proportional to k, that means that k will be increasing too. So D is our answer. Part 2. So consider a trial with the 45-degree ramp. Suppose a block is launched up the ramp such that it comes to rest at point B and then travels down the ramp. Which of the following best describes the block's kinetic energy Ka when it reaches point A at the bottom of the ramp in comparison to the initial kinetic energy before it travels up the ramp? So we know that before it travels up the ramp, so before it even touches this point right there, there's no friction, right? But we do know that when it reaches point A after coming back down, it has traveled through a ramp that is full of friction. And so friction is removing the mechanical energy because it's reducing the kinetic energy that's required. So since initially we don't have to worry about the y value being decreased, and we can see that the x is, or not the x, the k, the kinetic energy is increasing, that leaves our answer choice with B. If you want justification, we know that it's not C, no, it's not D. It can't be impossible to predict the kinetic energy. It can't be K A equals to KO or K initial because there's friction over here, but there's no friction here. We know that KA can't be greater since friction is reducing it, so that leaves us with B. Consider the trial in which the ramp is at a 20-degree angle with the horizontal. The surface of the ramp has been replaced with a surface in which frictional forces are considered to be negligible. If the mass of the block is doubled and the initial launch speed is double, how could the student predict the new vertical of the block at point B? So, first thing to note is that we replace the surface. So this is a whole new question in itself, where friction is completely negligible. So if I were to draw the diagram, we'd have some point here, we'd have some point here, and that would be a 20-degree angle with it would be a 20-degree angle with no friction. So since this whole entire system is frictionless, and we're considering just the surface of the ramp as a whole unit, we can use the law of conservation of mechanical energy to determine the vertical height. One thing to note is that we have since the block is originally over here and it's moving, the y value isn't changing, so the vertical position isn't changing, so the initial will be plus mg times the displacement in y, which is 0 since it's not changing. So this will be on the initial side. The final side will be the kinetic energy. So we will have 1/2 mv squared plus mg times whatever the displacement in y is. And so the displacement in y will be equal to h, as noted here. Final. So you may be wondering, why aren't we including this? Well, that's a good question. The reason is because these are going to be exactly the same, and since they're equivalent, since they're equivalent, this is just determining the final mechanical energy. You could actually just remove this since it's already conserved in one part. And so if we were to simplify this equation, it would be 1/2 mv squared is equal to mg times the displacement in y. To further clarify above, I put these twice, which isn't the smartest idea. Since it's already moving initially, we don't have to include it in the final since it's already there in the final part. So we could just neglect that. And so we get 1/2 mv squared, and then, yeah, we can solve for y final. Alright, a block of mass m is on an inclined surface is attached to a spring of neglectable mass as shown. The other end of the spring is attached to a wall and there is neglectable friction between the block and the incline. The block is pulled to a position such that the spring is stretched from its equilibrium position. The block is then released from rest. Which of the following systems can be classified as a closed system? Alright, so a system consisting of the block only. Well, why is this wrong? So the first thing to note is that if we were to think of just a block by itself, we would still have a gravitational, assuming that this block is on Earth, we would still have the gravitational force acting on it. And since there's a gravitational force, it changes the total mechanical energy. Thus, this is not a closed system. A system consisting of the spring and Earth. Okay, so the block is connected to the spring and its kinetic energy is converted into the spring's potential energy. And so in order for it to be considered as a part of a closed system, it would require that the spring be involved too. So if we just have the spring and the earth, or not the spring, if we just have the block and the earth, we're neglecting the force that the block applies on the spring, block to spring, and we're neglecting the force that the spring applies to the block. And so that is not correct. A system consisting of the block and spring. Well, as we mentioned above, we would still have the Earth's gravitational force. So with all three of these elements combined together, we have our correct answer, which is D. Alright, the total mechanical energy of a system as a function of time is shown in the graph. Which of the following statements is true regarding this system? So the first thing is observe the graph. Notice that the total mechanical energy does change. So the first thing we can note is that the energy isn't conserved, and since it's not conserved, it's not a closed system. And so we can instantly rule out A and D. Alright, so the system should be classified as an open system because the mechanical energy can be added and removed from the system. That sounds reasonable, so we'll leave it there. The system should be classified as an open system because the curve in the graph is symmetrical. Although this is the right answer, the reason that justifies it is not correct. Just because the graph is symmetrical does not mean that it should be an open system. Because if we were to think about it, if the total mechanical energy in time, if it were a straight line, and we were to split the graph, they're symmetrical on both sides, right? But that does not mean that it's an open system, so that rules out option B. Alright, next question. A planet orbits a star along an elliptical path from point X to point Y as shown in the figure. In which of the following systems does the total mechanical energy of the system remain constant? So, this is just one planet at position X and Y. And so, to answer this question, it would be best to use the law of deduction. So, let's see. Answer choice A says, the open system containing the planet. Well, if we were to just contain the planet, and it was an open system, mechanical energy does not remain constant. So we can automatically rule out A and B since it's an open system. So the closed system containing the planet. Well, if it were the closed system containing only the planet, so let's say we were to just focus only on this point right here, since it's still moving in its elliptical path, that would mean that the star is an external force on it, and so it's not a closed system. But if we were to put a closed system with both the star and the planet, then since the star or the only force acting on the planet is the star, it would be correct. So this is our correct answer. All right. A 5 kilogram object near Earth's surface is released from rest such that it falls a distance of 10 meters. After the object falls 10 meters, it has a speed of 12 meters per second. Which of the following correctly identifies whether the object Earth system is opened or closed, and describe the net force? So it has a speed. So the first thing that we should do when we see a problem like this is look at our initial and final. So E initial and E final. Okay, so initially, the only since the block is released from rest, that means it's initially at rest. Okay, the wording on this is a bit confusing. So we have 0 kinetic energy, so it'll be 1/2 m times 0 squared plus mgy, whatever m is. Sorry, that's my cuckoo clock. Okay, so this just equals to mgy as our initial. Now for our final, it is falling with some sort of velocity. So we get 1/2 m times 12 meters per second, or yeah, just 12 meters per second squared, plus m times the displacement in y, so whatever displacement in y is. And so let's use the law of conservation of energy. So they obviously cannot be equal to each other, telling us that this is an open system. So what we can do is we can already rule out answer choice A and answer choice C. Answer choice C doesn't make sense because the net external force is 0. That defies what the definition of a closed system is. So we could rule that out even before we did any work. So the system is open and the net external force is 0. The force could be 0, but still not be a closed system. But in this case, the net external force can't be 0 since the final and initial energy don't cancel out. And so it's not answer choice B. It is answer choice D. If we wanted to figure out the final mechanical energy, we could rule this out, and we'd have 1/2 mv squared, and we would get 1/2 of 144 is okay, you know what, we don't need to put that in. I believe it's around 360. It should be 360 joules of energy. Never mind, it's not 360 joules of energy. It should be 5 kilograms. I completely forgot. Okay, yeah, so we do have the mass accounted for over here. It would be 1/2 times 5 times 12 squared, and that would yield us 360 joules. All right, and so that is not equal to the initial since we know the mass and we know the displacement. We could do 5 times 10 times 10, which would get us 500 joules, and 500 joules is not equal to 360. Sorry, completely forgot to include the mass there, but it's okay, caught it. All right, next question. A toy car has an initial acceleration of 2 meters per second across a horizontal surface after release from rest. After the car travels for time t equals 5 seconds, the speed of the car is 25 meters per second. Is the system consisting of the car an open system or a closed system, and why? So, a good thing is to work with what we know. So let's look at definitions. Closed system, net force is equal to 0. Open system, net force is not equal to 0. That's the first thing we can look at. Where force is defined as mass times acceleration in this case. And so we're given the velocity, and we're given a time, and we're given an acceleration initial, which is 2 meters per second. We can call this V final, and actually no, we should not call it V final and T final. Well, it's in between the states, so it's at some instantaneous time. So we can find the acceleration at that time by doing a change in velocity over time. So this would yield us 5 meters per second, and since the accelerations are different, that would contribute to the overall force being different. So we know that it will not be a closed system, so we can rule out both C and D. Now, an open system, because the acceleration of the car is not constant. Alright, so this is potentially a right answer. Let's look at the next. Open system, because an external force is applied to the car that causes it to accelerate. So, in our open system definition, the net external force cannot be equal to 0, right? And so College Board provides you two answers that may seem right, but in reality you have to pick the best option. So this only says one part, but this says both parts. It's an external force and it causes an acceleration. So it has to be option B. Alright, for this one, let me see if I can turn my iPad vertically. A student performs an experiment in which a ball travels in a perfect circle. The ball is attached to a string and travels in the horizontal circular path as shown in figure 1. At time t initial, the ball has a speed of v initial. During the time interval 0 to 2 seconds, the force of tension in the string is recorded and graphed as shown in figure 2. Is the system consisting of the ball, string, and student, so ball, string, and student, an open system or a closed system, and why? Alright, so the first thing to note is that the force of tension is constant, okay? So we know that the ball string system would be closed. Actually, I lied. The ball string system will never be closed because we still have the earth acting, or the gravitational force acting on it. So, since we're talking about the student, string, and ball, but we never included mention of the earth, that tells us that it will be an open system since there will always be a gravitational force acting on the object. And so we can automatically rule out C and D. Now it's between these two answers. So open system, because a net centripetal force of tension is exerted on the ball that changes the direction of the ball. Or open, because the force due to gravity from Earth is an external force that is exerted on the ball string system. So in this problem, the centripetal force is between the string and the ball. And so in the answer choice terms, let me clear that out for you, it's an internal force. And so since it's an internal force, that does not justify it being an open system. So it would be B, because it does make mention of gravity from Earth. Alright. A block on a rough horizontal surface is attached to a horizontal spring of negligible mass. The other end of the spring is attached to a wall. The spring is compressed such that the block is located at position X. When the block spring system is released, the block travels to the right through position Y and continues to travel through the right through position Z. Free body diagrams for a block at position X, Y, and Z are shown in the figure. At which position does the block have the greatest kinetic energy? Alright, so first thing to note is that the normal force and the gravitational force are equivalent, meaning that there's no change in Y at all. So now we're only concerned about the kinetic energy of the system. So when it's compressed, there's no kinetic energy at all. You have the maximum gravitational potential energy. So we have max gravitational potential energy. And then when it's fully stretched out, there's no velocity, right? We have also the max gravitational potential energy when it's compressed and when it's stretched. So they would be equal. Oh wait, when it's stretched. But when it passes through, where the force of friction and the spring are even, we have the greatest amount of kinetic energy since there is some kinetic energy that's... Alright, so for this question, a 5 kilogram block moves with a constant speed of 10 meters per second to the right on a smooth surface where frictional forces are considered to be negligible. It passes through a 2-meter rough section of the surface where friction is not negligible, and the coefficient of kinetic friction between the block and the rough section is 0.2. What is the change in the kinetic energy of the block as it passes through the rough section? So, the first thing to observe is that this has negligible friction, so no friction, and that this has friction. So the change in kinetic energy from here, kinetic energy initial, which is equal to 1/2 mv squared, and kinetic energy, let's just say final, is equal to 1/2 mv squared here, will not be equal because there is friction. And since there is friction, that tells us that the kinetic energy of the initial will be greater than the kinetic energy of the final. And because of that, there will be energy removed. And we can view this as is greater than 0. So there is some energy removed, and it will be some positive remainder, but we are removing energy. And so we can automatically rule out C and D. Now it's time to get to the work. So we know that work is equal to force perpendicular to displace, or not perpendicular, it's parallel to displacement. And so we know that the work is also equal to the change in kinetic energy. And so the force, we have to account for the coefficient of kinetic friction. So it would be 0.2, and the direction is in the opposite direction since friction always works in the opposite direction. Remember that work is a vector and we do need to specify our directions. So we get work is, let me write that here too, is equal to UK, which is the force. Well, the force times mass times gravity, so the mass would be 5 and gravity would be 10, since College Board acknowledges it as 10, times the displacement, and the displacement would be 2. And so this is all equal to our work or change in kinetic energy. And so our change in kinetic energy yields negative 20 joules. Thus, 20 joules is removed from the block. Next problem. A rock of mass m is thrown off from the edge of a cliff from the edge of a cliff of height h with an initial velocity v initial at an angle theta with the horizontal, as shown in the figure. Point B is the highest point in the rock's trajectory, and point Q is the level with the initial position of the rock. All frictional forces are considered to be negligible. Which of the following could correctly describe the total energy of the rock-earth system at points P and Q? So, at point P, it's the highest point, right? So that means our velocity is 0 meters per second. And since our velocity is 0 meters per second, that tells us that our kinetic energy is 0, right? Well, unfortunately, this is where College Board tries to trip you up. This is the dilemma most kids run into. The answer to this dilemma is that there is a horizontal and vertical component of velocity. This refers only to the vertical component of velocity being 0. That is not quite right? And so we still have the horizontal component going this way. And so to account for point P, we still have the mass times gravity times whatever height it's at, plus 1/2 times the mass times the velocity squared, since we can account. So we could account for the velocity in the horizontal component as horizontal velocity equals to v initial times cosine theta, which would get us this right here. And so we got point P. Now point Q. Well, point Q is still suspended in air, so we will still have our potential energy here. Plus, and it's still falling down with a horizontal and a vertical component, so plus with 1/2 mv squared. So the equations for these will be the same, and our answer choice is C. A ball of mass m is attached to a spring of neglectable mass that has a length r. The ball moves clockwise in a vertical circle as shown above. Which of the following is true about the ball string Earth system as the ball moves from point 1 to point 2? So, when we look at our answer choices, it's talking about the potential energy decreasing. Now, there's no doubt that the potential energy decreases from point 1 to point 2, because if we were to say that this is y, then for some quantity k, this point would be y minus k for the height. And so it will 100% decrease, so we can keep that in mind. Now, by how much it decreases, we don't know. So we know that at point 1, the total mechanical energy is equal to, should be equal to mg y, or you know what, let's put h. mgh plus 1/2, or the tension in the string would still be 0, because at this point, actually no, it's not equal to 0 at sorry, I'm tripping right now. It would just be mgr, because that's just how much the tension is. So same thing here. Okay, we can just cancel that out. At point 2, we have the mechanical energy neglecting, you know what, I could just say potential energy, since we're not really accounting for kinetic energy at this point. We're only talking about potential energy. So potential energy would be equal to mass times the gravity. Now, in contrast to point 1, it would be, since we have our radius, or over here I should have actually said minus r. Since we're talking about the radius, we know that 1 should be 2 times greater than 2. So 2 is 1/2 of the height of 1. So what this means is that our potential energy is decreasing by 2, because we originally have it at r. So if we call this the initial position, and we go down with r once, and then again, we have 2 mgr. So it's really mg times 2 times r. And so we're decreasing the tension by that, or we're decreasing the potential energy by that, and the tension in the string will be increasing by more than 2 mg, because because we are now holding the block going down this way. The mass is since we have our constant r, it'll be 2 times the mass times earlier, as we said, y minus k. So our answer choice is D. Alright. A small block of mass m equals to 0.10 kilograms is released from rest at point 1 at a height h equals 1.8 meters above the bottom of a track as shown in the diagram. It slides down the track and around the inside of a loop of radius r equals 0.6 meters. The speed of the block is 2.5 meters per second at point 3. Which of the following claims about the situation is correct? So the gravitational potential energy of the block Earth system at point 3 is less than the gravitational potential energy at point 2. Now, we could sorry about that. Well, we can't really compare point 3 and point 2. Well, we can compare it, but it doesn't make sense since we have a greater y, right? So if mg, y, and we subtract the radius, mg, y minus r, that means that this will obviously be smaller for point 2, and this is point 3, so point 3 is greater than point 2, and so this makes the statement false. Sorry, I glitched for a second. The kinetic energy of the block at point 3 is greater than the kinetic energy of the block at point 2. Well, we already know that the potential energy, we know it's conserved if we were to just think about this system. And so we already noted that the gravitational potential energy is greater here. So that would mean that the kinetic energy is less at point 3 than it is at point 2. And so that is the exact antonym of what this says. So B is wrong. The mechanical energy of the block Earth system at point 3 is less than the mechanical energy at the block Earth system at point 1. Now this is evidently true since the y is greater. And so C is a correct answer. And we can rule out D because it can't be equal. It's not equal to different altitudes. Object X and object Y are connected by a string of neglectable mass and suspended vertically over a pulley of neglectable mass, creating an at-will machine as shown in the figure. The objects are initially at rest, and the mass of the mass of object Y is greater than the mass of object X. As object Y falls, how does the kinetic energy of the center of mass of the two-system object change? Justify your selection. All frictional forces are neglectable. So the initial will be when it's at rest, and the final will be when it's moving. So let's just place, since we know that the mass of Y is greater than the mass of X, let's just place the center, let's just place the center of mass over here. Let's just put it over here. So now let's visualize it. As object Y goes down, it's going to accelerate, okay? And it accelerates because it has a greater mass, and it accelerates due to the gravitational force. And so that tells us that this point right here is going to accelerate going this way, right? So that tells us that the kinetic energy, since it's accelerating, that means our velocity is also increasing. That tells us that the kinetic energy is increasing, since kinetic energy is equal to 1/2 mv squared, and if the velocity increases, so does the kinetic energy. And so we can automatically rule out C and D. So let's look at the next part. So if we divide them, we see that one does positive network on the system and one does negative network on the system. Well, the mechanical, the mechanical energy is, the mechanical energy is defined as, work is defined as force times displacement. Wow, I've glitched quite a lot just now. Okay, so since the force and the displacement, since it's going down, we can say that the force is negative, right? The mass times the acceleration, we can say the acceleration is negative since it's going down. The force times the displacement, since it's going down, is negative displacement, is equal to work. That tells us that a negative times a negative is equal to a positive, so our work will be positive. To explain that in deeper terms, we get F equals to ma, right? Now, since our acceleration is going down, it's F equals to m times negative a, or negative F equals to ma, right? And so that's our force. Now, our displacement is equal to, well, velocity equals to displacement. I'm not sure if this exactly correlates, the statement over time. Our velocity times the time equals to the displacement. So our velocity is increasing, that means our displacement is increasing, but our velocity, since velocity is a vector, we have to account for the sign, right? So since we have a negative velocity, since it's going downwards, we have negative vt equals to, I meant to write d, is equal to the displacement. So that tells us that our displacement is equal to vt, and it's negative. And so work is equal to force times displacement. So if we have a negative force and a negative displacement, that means you have positive work. So that rules our answer choice A and knocks out B. Alright, a small object of mass m is horizontally shot horizontally from a spring launcher that is attached to a table. All frictional forces are considered to be neglectable. The ball strikes the ground a distance d from the base of the table as shown in the figure. A second object of mass m over 2 is launched from the same launcher such that the spring is compressed the same distance as in the original scenario. The distance from the base of the table that the object lands is... Okay, first thing to note, yeah, okay, the first thing to note is that we have a different mass and that all frictional forces are considered to be neglectable. So that means that we're neglecting drag forces. So we will have k equals 1/2 mv squared. And so the distance that the distance from the base of the table that the object lands is. So we know that our velocity is equal to displacement over time, right? And so if we observe this, velocity and displacement are directly proportional. And so let's say if the displacement increases, so does the velocity. If the velocity increases, that means that the displacement must be also increased. And so we could solve for this in terms of v. And so if we were to do that, we would get v is equal to 2mk, 2 times the kinetic energy divided by the mass, and we would square root this. Oh, I already wrote velocity. Okay, so if we have a mass m over 2, that means that we have, okay, so this is the initial, so this is when the object just has a mass m. But if we have a mass m over 2, that really means that we have, sorry, this whole thing should be under the radical 1/2, same thing. 4 times the kinetic energy over m. And so if we have 4 times the kinetic energy, if we were to just square root the 4, we just get 2, or actually no, that's the wrong way of thinking about it. If we were to break it up, we would get v equals to 2 times kinetic energy over mass, and square root all of that. So that means that we have an increase factor of root 2, right? When the mass over 2 is there. So it's greater by root 2. So our only answer choice is C. Okay, well, I'm feeling pretty bad after making this video because I stuttered way too many times. But I guess you live and you learn and you get better at practice. Thank you for watching, and yeah, have a good day.